right, so we're going to be looking at section 9.3, sequences. What is a sequence? Sequence is an ordered progression of numbers. Here's the definition of a sequence, and I'll go ahead and write this out, read this to you. So, definition of a sequence. There's an infinite sequence if a function is a function whose domain is the set of positive integers. The function values, which are designated this way, it's like each of these is a term. A sub 1, A sub 2, A sub 3. This is so you can just distinguish between each term, and it's in order. It's an ordering progression. Each item in the sequence is a term. If the domain is restricted to the first n integers, so if it stops here, then the sequence is a finite sequence. That means it stops. If it keeps on going, then obviously it's an infinite sequence. Sometimes for convenience, they'll start the first term at A sub 0 instead of A sub 1. You'll see that periodically, okay? But it doesn't really change the sequence at all. We can write rules or equations to express sequences, and we're going to do it in two ways. We're going to do it either explicitly or recursively. An explicit rule is a rule that is based on the integer value of the domain or the position of the sequence term. So in other words, we're going to write a rule so if I tell you I want the fifth number in the sequence, then I can plug 5 into the formula, into the explicit rule, and I will get the number that's in that sequence. Okay, so it's based off the position that the item, that the term is in. The recursive rule is based off of a pattern where I recognize how to get from this term to this term because there's a pattern. It's the same pattern for each term. And so then it allows me to get the next answer based off of previous answers. So that's what a recursive rule does. It gives you an answer in the next term based off of previous terms in the sequence. So here's an example right here we're going to do. Here's a sequence. Let's see if we can find the explicit and recursive rule. So usually what I have people do when they do this is I ask them to take these things. This is a function. Let's put these things into a table. If I make a table, then we use, instead of x and y, we use n for the number in the sequence. And a sub n represents the number in the sequence. So this is n, it represents the position, and a sub n represents these numbers. So the first number in the sequence is the number 1. The second number in the sequence is 4. The third number is 7. The fourth number is 10. And so our goal here is to figure out how I can find the 5th, the 6th, the 7th, the 100th term in the sequence. Okay? And so the next thing that we do is we look for some kind of pattern associated with this. And so the first thing I tell people to do is let's look and see if there is an addition or subtraction pattern. To go from here to here, because these are integers, these are always going to be plus 1 in this scenario. So can I find a number that will add to get to 4? That's the same value for all of them. So in other words, I notice that 1 plus 3 is 4, and 4 plus 3 is 7. So it's looking like I have a repeated pattern here of adding 3. Okay? So the next thing then is to write in the rule for this thing is let's go ahead and look at for the explicit rule. Okay? I see a pattern associated with this. It's adding 3 each time to get to the next number. And so can I get a rule? Can I see how I can use that 3 to get from here to 10? Okay? And usually if you see a repeated thing, repeated addition, if I add the same number over and over and over and over and over again, that is similar to multiplication. Multiplication is repeated addition. I'm going to have a 3 this many times. So think about this right here as my position. Since I am repeatedly adding 3, that means to multiply by 3. So I can just take, well, what is 4 times 3? 4 times 3 is 12. To get to 10, I would need to subtract 2. So a possible rule would be to multiply the position number by 3 and then subtract 2. Let's see if it works for the other ones. Take this number, multiply it by 3, you get 9, subtract 2, I get 7. Multiply this number by 3, I get 6, subtract 2, I get 4. Multiply this by 3, I get 3, subtract 2, I get 1. So it looks like that might be my rule for explicit rule. 3 times whatever the position number is, and then subtract 2. Well, what about a recursive rule? The recursive rule is based off of how do I get to the next number? How do I get to the next number? And again, the pattern we see is that we just keep adding 3. Now the recursive rule, you have to have a starting position, some place to start. And you always start with the first number in the sequence. The first number in the sequence is 1. You need that also. Otherwise, the recursive rule doesn't make sense. So then how do I get to the next number? How do I get to this number? Somewhere out here. Well, how do I get to the next number here? I take the previous answer and add a 3. So the next number is the previous number. This is about position. If whatever position this number is, this is the one before it, and then add 3. So that would be the recursive rule. Okay? So let's go take a look at some more information of what we might be able to glean from some of this. So this is what I just wrote. I have some side notes here, so you can pause it here and write that out. There's 2 major sequences that we focus our attention a lot on at this stage in math. Later on, you'll go into other types of sequences and stuff. But for now, we're going to be looking at the 2 major ones, which are arithmetic and geometric. So the arithmetic is the sequence we just looked at. The arithmetic sequence is a sequence if the differences between consecutive terms are the same. So in other words, up here, this was a arithmetic sequence because 4 minus 1 was 3, 7 minus 4 was 3, 10 minus 7 was 3. So you subtract consecutive terms, and if you get the same number every single time, then it is an arithmetic sequence. Subtract consecutive terms, and you will get the same number. If that happens, it's an arithmetic sequence, and D is what's called the common difference. Okay? You'll notice that this thing right here looks very similar to y equals mx plus b. That's because arithmetic sequences are linear in nature. They are linear in nature, and the common difference is kind of like the slope. So the recursive rule is the first term, identify it, and then the next number is the previous answer plus the common difference, which is what we had right up here. The previous answer plus the common difference, which was 3. Notice the 3 is right here. This is kind of like the slope, right? Mx plus b, so x would be the n value. This is the slope. And you'll look, it looks very similar to the point slope formula on finding equations of lines. So that's why it looks like it does. The explicit rule can be found from any position in the sequence. Most commonly, it's used using the first term. If I have the first term, the next number, any number in the sequence can be found by taking the first term and then adding the common difference times this quantity, n minus 1. But if I take any term in the sequence, then this a sub k is the any term in the sequence, and k is its position. See, a sub 1, and it's in the first position. A sub k is in the k position. So that's the modification to the rule, and it will give you the exact same answer each time. That is arithmetic. So let's look at another example and do this one. Find the explicit and recursive rules of this sequence. So when you first look at a sequence, you do not know if it's arithmetic or not. So you need to kind of determine that. The best way to determine it is to put it into a table. This helps you do a lot of things. You never know, they might ask you to graph the sequence and so forth. The third number is 16, and the fourth number is 23, and the fifth number is 30. If you were to graph this, I know I'm not talking about that now, but if you were to graph the sequence, it is just a series of dots. You do not connect the dots with any curve or anything. All right, so I have this. Each of these is a +1. Each of these, we'll see if there is a common difference. It has to be the same number every time to be arithmetic. 2 plus what is 9? 2 plus 7. 9 plus 7 is 16. 16 plus 7, so it's looking like 7 is our common difference, is 7. Okay, because I have that, I'm good to go. We can do our explicit rule. The explicit rule is very simple. It's going to be a sub n is the first number in the sequence plus the common difference times n minus 1, because I used the first number in the sequence. You just need to multiply this and clean it all up. Multiply that, clean it all up. I'll show you the work for this one. And so a sub n is 7n minus 5. Okay? What is our recursive rule? I need to know the starting value. Where does it start? It starts at 2. And then how do I get to the next number? The next answer is the previous answer plus 7. So the next answer is the previous answer plus 7. And so that is the recursive rule right there. All right? Let's look at the geometric. The geometric sequence has a ratio between consecutive terms that is the same. So literally that means I'm going to take two consecutive numbers and divide them. So A2 divided by A1, A3 divided by A2, and so forth and so on will give me a common ratio that we call and designate by R. If this occurs, I have a geometric sequence and a common ratio of R. And like arithmetic was linear in nature, a geometric sequence is exponential in nature. Okay? If you don't remember what exponentials look like, these are the graphs that do something like this. It can go like that, or it can come down like this. So these are exponential in nature. So you'll see a lot of similarities in the rule setup, recursive rule. Gotta have a starting point. And since exponential, exponent rules and stuff like that is just repeated multiplication, that's why once we have a common ratio, we multiply it to the previous answer. So you're multiplying to get to the next number or dividing. Think of it as multiplication. So you're multiplying by a number or you're multiplying by a fraction. If I want to use the first term for explicit rule, it is the first term times the common ratio in parentheses raised to the exponent n minus 1. If you want to use any term in the sequence, Take any term of the sequence and find its position and to be n minus that position k. So with this, let's look at an example right here that I have over here that is geometric in nature. But we go through the same process. I don't know this is geometric until I show that it's geometric. So same thing as always, put it in the table. First position is 9, the second one is -6, the third is a 4, and the fourth is -8/3. We need to confirm that this is indeed geometric by finding the common ratio. So I can just take these consecutive answers, -6/9, reduce that, take 4 divided by -6, reduce that. It's looking like it might be -2/3. Take a -8/3 divided by 4. And if I do the fraction and work over here, you'll find out that this is indeed a -2/3. You should check that out, make sure you can see that. What that basically means is, from here to here, I am timesing by -2/3. Take that, times it by -2/3, and so forth, and so on, times by -2/3. So my common ratio is a -2/3. Once I have that, then I have all I need to write the rules. The explicit rule, a sub n is the first term times the r always in parentheses, and then n minus 1. And there you go. The recursive rule, I need to know the first term, and then the next term is the common ratio. You can probably put it in parentheses, times the previous answer. And there you go. Recursive rule, explicit rule. Now changing course just a bit. Into a lot of functions that we had, especially like exponential functions, log functions, things like that. Rational functions. We were interested in the end behavior of functions. What is happening on the ends of functions? Well, we are also interested in what is happening on the ends or the extreme parts of a sequence. So what happens if I keep on going to an infinity sequence? Okay, and that is a thing called a limit of a sequence. This symbol right here is a way to describe a sequence. The curly brackets with an a sub n in it means that I have a sequence, and it just keeps on going. So let this be a sequence of real numbers. It's a limit as n goes to infinity. So in other words, I'm looking at the far end on the right, because the left side is set at a sub 1. So there is no negative infinity. It's only a positive infinity action. As the counting number down here, the position number goes to infinity. So we're having infinite sequence. Okay. If that limit, in other words, if these numbers in the sequence get closer to a finite number, then the sequence is said to converge. And L is the limit of the sequence. If the limit is infinity or non-existent, then the sequence diverges. And I'll show you how this looks and works out in just a moment. So let me pull up my problems here that we're going to look at. And I'll walk you through how to do these. So determine whether the sequence converges or diverges. If it converges, give the limit. So here's a sequence. It goes on forever. I want to know, do these numbers get closer and closer to a single number is what I'm looking at. And to do that, you want to find the explicit rule of the sequence, if you can. And to help us find that, we got to determine what kind it is, so we make a table. Second, third, fourth position, 2, 5, 8, 11. And I can see fairly clearly here this is a +3 all the way across. So that means this is arithmetic in nature. The common difference is going to be 3. So my explicit rule, you want to find the explicit rule, not the recursive, just explicit, is going to be a sub n, 2 plus 3 n minus 1. And then when you clean this up, you're going to get 3n minus 1. So what they're saying in our information over here, we want to find that. So a sub n is the explicit rule of the sequence. I want to take the limit as n goes to infinity, and I'll show you how that works. So we want to find the limit as n goes to infinity of a sub n, which is 3n minus 1. So to find a limit like this at infinity, what you want to do is you want to think, what happens at a really, really, really large number? And I always tell people, don't even think about any number below 1 million. Okay? So what if n was 1 million? If n was 1 million, then what would this be? What would this expression be at 1 million? Well, you just literally plug in 1 million for n. You would get 3 times 1 million minus 1. Well, that's pretty close to 3 million, isn't it? Minus 1, so you can ignore the minus 1. That really doesn't matter. And then what happens when n is, 1 billion? Well, then this number here would become 3 billion. Is that number getting close to a single number? Or does it just keep getting bigger and bigger and bigger? If I pick another number bigger than 1 billion, am I going to get a number that's getting closer to some other number? No, it's just going to keep getting larger. So when it does that, if it just keeps getting larger and larger and larger and larger, then that limit does not exist. And so this thing diverges. So the limit as n goes to infinity of 3n minus 1 just keeps getting larger. It goes to infinity. It's getting bigger and bigger and bigger. So that means this diverges. Okay, let's look at this one down here. This one's a little bit tricky if I put everything into a table because we don't know what it is. We got 1/2, 1, 5/4, 7/5, 3/2. Okay. If I do this, I can see clearly that it's not the same number. I can't add the same number both times to get to the next one. That's not going to work. I can't multiply. So this times 2 is 1. That times 2 is not that. So it's not geometric. So this is another. This is one of those sequences that are a little bit harder to see. And it just takes practice to try and figure these things out. Here's some suggestions that I usually give. Notice that all the numbers in the sequence most of them are fractions. If they're fractions, can we make them all fractions? Can we do that? And if that's the case, then what we want to do is we can look at this as, okay, find a rule for the tops of the fractions, and then find a rule for the bottom of the fractions. Okay? And you might need to change some things around. Like this was a fraction that was probably reduced. So let's unreduce it. Okay? And keep it in line with everything. And you start looking for a pattern between this and this. Like this is a whole number, which means it was probably a fraction. Right? And so what fraction would it have been? You can try different fractions in here to see what you would have gotten, change the denominators to different things. And in doing so, you would have realized that this one right here is probably 9/6. And then this right here would have been 3/3. Because then look, the bottom numbers are 2, 3, 4, 5, 6. And you can see a pattern in that fashion. And then the tops have a pattern too. 1, 3, 5, 7, 9. Okay, and with that, then I can see that I can probably find a rule. So that, and you do them separately. So the bottom number, based off of 4, how can I get the bottom number? Well, I just simply add a 1. So whatever the n number is, the bottom is going to be n plus 1. And the top are odd numbers. And odd numbers follow a certain pattern. Even is always, an even number means it's divisible by 2. So that's usually even numbers are written as 2n. Those are even. And so the odd would be 1 more or 1 less than this. So if I have a 2 and I times it by 2, I get 4. So to get to the 3, I would need to subtract 1. 3 times 2 is 6, minus 1 is the 5. And so that's how you can find a pattern in its fashion. Again, this is a little bit more challenging. You're mainly focusing on arithmetic and geometric sequences. This is just another sequence to show and illustrate the convergence and divergence aspect. So what is the limit as n goes to infinity of that sequence rule? And so we do the same thing. What happens when I plug in a large number? Okay, so let's plug in a million. If I plug in a million, this expression right here becomes 2 million minus 1 and 1 million plus 1. Does the minus 1 and plus 1 matter really in the big scheme of things? If you think it does, then let's make this 200 trillion minus 1. If you have $200 trillion, do you care about a dollar? I don't think so. So really, these things on the end here become insignificant. And this just basically boils down to getting closer and closer to the number 2. 2 million divided by 1 million is 2. 2 trillion divided by 1 trillion is 2. See how it's getting to the same number? So we say that this thing equals 2. And so this sequence will converge and the limit is 2. And so that's how that works. Okay? So here is a picture of my notes for those who want to pause it and write down what I wrote back here at the bottom. Let's start here. So I'll put it here, and you can pause it and write that down. And then I'll put it here, and you can pause it and write that down. And if you have a hard time getting that, just let me know, and I'll let you get it in class. Okay? So that's what we're going to be doing, and we'll do more in class.